we were discussing hierarchy of convergence, right. So, we were talking about various notions of convergence and which of these notions imply the other and so on, hierarchy of convergence concepts. So, the main result we had was that almost sure convergence and rth mean convergence, they both imply convergence in probability, right, and convergence in probability implies convergence in distribution. So, generally none of the opposite implications are true in general, okay. None of the reverse arrows hold, generally speaking. However, if you have, so in this, for this reverse arrow for example, it does not hold generally, but if your limit is a constant, then convergence in distribution implies convergence in probability, okay. So, if the limit is a constant, x is a constant, then these two notions are equivalent, okay. Then we also proved this bit. So, we are done with that bit, okay. Did we give a counter example to this? So, okay. So, you can construct a counter example to this, it is actually fairly trivial, we will do it. And then we constructed a, so this proof we have done. So, almost sure implies convergence in probability, we will do today. So, it is a non trivial proof, okay. And the reverse arrow is not true also, we have given a counter example, okay. So, I have to give you a counter example for this I gave you, and for between these two I have to give you a counter example, right, neither way is the implication true, right. So, so where we left off last time was, if you consider, so you consider the example where xn is equal to 1 with probability 1 over n, 0 with probability 1 minus 1 over n. We showed that xn converges to 0 in probability, but xn does not converge to 0 almost surely, right. So, here xn's are independent. So, this is the counter example we gave, right, to show that convergence probability does not imply convergence almost surely. We used in fact Borel-Cantelli lemma to assert that it is not true that beyond a point. So, even no matter how far out you go, there will be some xn which is equal to 1, right, which means xn does not go to 0. Is that argument clear? So, this Borel-Cantelli lemma also gives us a sufficient condition to check for convergence almost surely, okay. So, if you think about convergence almost surely, it is conceptually easy enough. So, it just says that you go look for all omegas where this convergence happens. If the set of omegas where this convergence happens has probability 1, you are fine, right, then converges almost surely. But this is not a very practical definition, right, you have to go and hunt for all, right, you have to see which or where does the convergence happen, where does the convergence not happen, and look for its probability, right. It is not a very practical way of ascertaining whether the convergence almost surely occurs or not. So, what we will do is today we will derive a simple sufficient condition for convergence almost surely, and we will derive a necessary and sufficient condition for convergence almost surely, okay. So, sufficient condition for checking whether xn converges to x almost surely. If for all epsilon greater than 0, sum over n equals 1 to infinity, probability then xn tends to x almost sure. Okay. So, this is a easy condition to check. So, if you notice this, so if you notice just that object, it looks like so this is what this term, if you prove that this term goes to 0, then it is convergence in probability, right. So, if this term goes to 0, you have convergence in probability for every epsilon greater than 0. This condition is a little bit stronger, it says a little bit more, okay. As n tends to infinity, not only does this term go to 0 for every epsilon, it goes to 0 fast enough that the sum converges to some finite value. Is that clear? For example, if this probability were to go to 0 as 1 over n, you will have convergence in probability, but 1 over n does not sum to any finite value, right, it is infinite. So, if this term goes to 0, not just goes to 0 as n tends to infinity, but goes to 0 fast enough to keep the summation finite, then you have convergence almost surely. Is that clear? So, this is a very easy way to check for convergence almost surely, but this is only a sufficient condition, okay. This is only a sufficient condition. If this holds, you are guaranteed almost sure convergence, but even if it does not hold, sometimes you may have almost sure convergence, okay. So, it works only in one direction. How do you prove this? So, it is a fairly easy proof. Right. So, you have to use Borel-Cantelli lemma. If you see a summation like that, you have to use Borel-Cantelli lemma, right. So, you call that event, let us call this event a n of epsilon, okay. A n of epsilon is the event that the absolute value of x n minus x exceeds epsilon, okay. By Borel-Cantelli lemma 1, only finitely often does a n of epsilon occur for any epsilon, correct. So, by Borel-Cantelli lemma 1, we see that for any epsilon greater than 0, a n of epsilon occurs only finitely many. So, what I want to say is, for any epsilon greater than 0, only finitely many a n of epsilon occur with probability 1, right. You agree with that? So, I have sum over n equal to 1 to infinity, probability of a n is finite. So, only finitely many a n's will occur by Borel-Cantelli lemma, and this is true for any epsilon greater than 0. Why? Because that is what my, if for all epsilon greater than 0 I have this condition. So, for all epsilon greater than 0, only finitely many a n's of epsilons occur. So, what does that mean? It means that for any epsilon greater than 0, there exists some n naught beyond which none of the correct, right. So, which means beyond that n naught, absolute value of x n minus x is less than epsilon. So, x n has converged to x, and that is with probability 1, correct. You see the proof. So, this Borel-Cantelli lemma is very powerful sometimes in proving this almost sure convergence, okay. Thus, for any epsilon greater than 0, the difference x absolute value of x n minus x so what I want to mean, so I am saying this in a sentence, the difference remains less than epsilon for all large enough n, right. So what I am saying is, so there are all these x n's, right. So this is let me just consider x n minus x as my what I am plotting, right. So and if this is my, I am considering this band of width, this is epsilon, okay, this width is epsilon. What I am saying is there will only be, so this, so if I am plotting here the difference x n minus x, right. So there may be, some excursions, right, as n goes, but what happens is there must be some n beyond which it stays within, it forever stays within this epsilon band, right, it never exceeds this epsilon band, and this is true for every epsilon greater than 0, which means almost surely x n converges to x. You see this picture, so this is the difference that can jump around. So this is your epsilon band, you fix any epsilon you want 0.0001 and then it keeps jumping around, but Borel-Cantelli lemma says for with probability 1 there exists an n beyond which these excursions never occur, because only finitely many excursions occur outside epsilon, only finitely many excursions outside epsilon occur. So this sequence is doomed to stay within this epsilon band forever, no matter how small you take your epsilon, eventually it will get in and never get out, which means almost surely convergence has occurred, right. But this is only a sufficient condition, okay, fine. So it is, so I leave it as an exercise to you to figure out a situation where convergence almost surely happens, but this situation is violated, this condition is violated. So if this condition is violated, you are guaranteed almost sure convergence, but you may have almost sure convergence without this condition holding. You see what I mean? Okay, you create such an example, actually you already know that example, okay, you just have to recall it, okay. What I am trying to say is try to break the converse of this theorem, converse does not hold. Okay, great. So that is a very simple sufficient condition to check for, okay. In a similar spirit, next I am going to do as necessary and sufficient condition for convergence, okay. It will essentially exploit this picture, okay, necessary and sufficient condition for almost sure convergence. So okay, before I move to this, I want to make sure you have understood this sufficient condition, because the necessary sufficient condition is a little more involved. If you do not understand this, you will have a hard time with what I am going to say. Any questions? Okay, theorem. Let So, I am going to call the same a n of epsilon is the event that this excursion happens, right. So, same as this, okay. Let a n be that event and b m of epsilon is equal to union n greater than or equal to m a n of epsilon. Then x n tends to x almost surely, x n converges to x almost surely if and only if probability of b m of epsilon goes to 0 as m goes to infinity. So, this is a necessary and sufficient condition, okay. So, whenever something is necessary and sufficient, it is like equivalent statement, right. X n tending to x almost surely is equivalent to saying that my b m of epsilon has a probability that is going to 0, okay. See, note that a n of epsilon, probability of a n of epsilon going to 0 is convergence in probability, correct. Now, I am saying a little more, I am saying a little something is, so I will help you interpret this. Oh, so there is one mistake I made, I think b m of epsilon tends to 0 as m tends to infinity for all epsilon greater than 0, okay. This is true for every epsilon, okay. Okay, so now I will help you with the statement. So, a n of epsilon is clear, a n of epsilon is the event that there is at least an epsilon excursion of this difference at the nth value, correct. This is the nth term of the sequence. So, this difference exceeding epsilon means a n occurs, a n of epsilon occurs. Now, what is b m of epsilon? It is the union n greater than or equal to m a n of epsilon. So, can you explain in words what b m epsilon means? You fix an epsilon, no problem. Then what is b m of epsilon? Sorry? So, this is union over n greater than or equal to m. So, you are unioning over m, m plus 1, m plus 2 and so on, right. So, in words then b m of epsilon is the event that at least one excursion happens after m, m or after, right, correct. So, a n of epsilon is the event that at n. So, if you are looking at a particular n, right. So, this is the n axis if you look at figure, right. So, you are looking at the event that this difference has exceeded epsilon, right, x n minus x has exceeded epsilon, that is your. So, a n epsilon just looks at n, whereas b m of epsilon says you fix an m, fix an epsilon and then you say b m occurs if there is even one excursion m or after. Is that clear? Okay. This just means there exists an n greater than or equal to m for which the excursion happens, the greater than epsilon excursion happens, okay. Any questions on this? This is very crucial. Everybody with me? Okay. So, what this theorem says is, if the probability of this event goes to 0, then you have almost sure convergence. So, if the probability of the event that, so x n tends to x almost surely if and only if beyond m no epsilon excursions ever occur, okay. If you find some m, right, this m can be very large, but if you find some m beyond which no epsilon excursions ever occur after that m, then you have almost sure convergence and vice versa, okay. It is an if and only if condition, it is not a sufficient condition, it is a necessary and sufficient condition, okay. Any questions? Will I repeat anything?
Frequency of occurrence for A and epsilon should go down fast enough.
Yes, no, that was the sufficient condition. So, A n of epsilon, so you understand what this figure is, I am plotting. So, this curve is this whatever I have drawn here is the difference x n minus x, I am plotting it versus n, right, and I am saying that okay, let us say this is my n, if the difference between, if this difference x n minus x exceeds my epsilon band, then I say, so this is actually not absolute value of x n minus x then, right, it is only x n minus x, right, okay, fine. So if this difference exceeds epsilon, I say a n occurs, a n epsilon occurs, okay. Now we know that if, see, a n epsilon probability of that going to 0 is convergence in probability, right, that is clear to everyone, but convergence almost surely needs a little more. It not only needs that the probability of a n of epsilon goes to 0, a n of epsilon is the event that there is the, at n there is an excursion, right, but we are saying that Bm of epsilon has to have probability going to 0. Now this Bm of epsilon is the event that there exists some m beyond which no excursions occur, okay. So Bm of epsilon is the event that there exists, so Bm of epsilon is the event that there exists an epsilon excursion m plus 1 beyond m, correct. If the probability of an excursion at m or beyond, if that probability goes to 0, you have almost sure convergence and vice versa, okay, it is a necessary and sufficient condition.
Beyond that n naught, there will not be any occurrence for n, so this m will be related to that n naught, right?
Yes, that is what we are saying.
Okay, so from here sufficient condition is going back there.
Sufficient condition, see, sufficient condition, yeah, so this essentially tells me that there are only beyond some, so beyond some m there are no more incursions, that is what, so there are no more excursions, what this guy says, right. Now I am saying this is a little more strong.
Before n naught, just put some constraint. Right?
Before, no, see, this is a sufficient condition, this is a necessary and sufficient condition, okay. So this will be a, this will say more than that, okay.
Before n naught, before by BCL lemma, beyond n naught it does not occur.
Yeah, after some, so this result holds because by Borel-Cantelli lemma there exists some m beyond which there are no further excursions, right, therefore it converges. Here what we are saying is it is necessary and sufficient that Bm of epsilon has the probability tending to 0, okay.
Probability of Bm of epsilon is same as the first one with n equal to m to infinity and equal to 0 instead of n less than infinity.
No, it is not. So I will prove this. I will say this is probably the, I mean, so this is probably the most challenging or demanding proof you will have to understand, okay. I mean there are harder theorems than this which we will not prove, okay, but I think you should understand this much. Under convergence almost surely you should really appreciate what is going on, which is why I am doing this proof, okay.